have one electron, so if I have one electron in a wire, so this will not, this does not form a steady state current. Okay, so only one electron. So I need to have, so if I take a wire, I should have electron at each and every point on this wire, which will give rise to a steady state current. Okay, so though all the electrons have to move, they have to move at the same speed. Okay, and then I will get a steady state current. So this kind of current will produce basically your magnetic field. Now, there are two things which, when we talk about magnetostatics, we should be or we are familiar with. So, for example, so when we think of, so one is like the magnetic field that is produced due to this steady state current. Another thing is, if I have any electric charge, so this is going to feel a force due to either it can be electric field or due to a magnetic field. So the force on any charge particle. So let's say we say this is the charge particle has a charge Q. So the force due to an electric field and a magnetic field, the combined force or the resultant force will be QE plus QV cross B. So this is known as your Lorentz force. So this is a force that any charged particle will experience in presence of an external electric field and a magnetic field. So that means to have this magnetic force, so the charged particle has to should have a velocity. So only if a charged particle has a velocity, then only there will be a magnetic force. Otherwise, a magnetic force will be zero if the charged particle is at rest. And this is one aspect of this electric field, combined effect of electric and magnetic field on a charged particle. And the consequence also, like what you are familiar with, is this magnetic field, or the if you move a charged particle in a magnetic field, so this is not going to do any work. Why? So you can calculate the work done due to the magnetic force alone. So let's say if we just say what is the work done due to the magnetic force, which is your QV cross B dot dl. And always remember this dl is of this form, v into dt form. So this is the velocity and the infinitesimal time dt. So this is your the length vector dl. So that means when you take a dot product, so this is v cross b, which is always perpendicular to both the magnetic field and the velocity, and you take a dot product with the velocity, so this will be always zero. So that is why the magnetic force does not do any work. Okay, so this is one aspect of magnetostatics. And now when you have, so when you are moving a charged particle, and if it is, as I said, if you have a steady state condition, so you so due to the flow of these charges, so what you can generate is something known as a current and current density. So due to this movement of charges, so we produce something known as a current. Okay, and the And most of the time in electromagnetism and electrodynamics, we talk about current density. So which is basically your, so this is your current I, so current density J, which is number of charges that cross a unit area per unit time. Okay, so this is your charge density. So this will be in ampere per meter square or centimeter square, so depending on the unit that you are interested in. So this is the current per unit area. So that gives rise to a current density. And current density is always, it is a vector quantity. Okay, so and this current density, as we said, is it depends on the velocity of the charge. So because it is proportional to the current, and the current is nothing but when we look at a cross-sectional along the cross-section, how much current is flowing. So it depends on, so you can calculate it in terms of a charge density, which is given by this relation rho into V. So here rho is your charge density and V is your velocity. So what we are assuming is a steady state condition. So that's why all charge particles, so they are moving at the same speed or a velocity V. So this is a relation between your charge density and current density, J equal to rho into V. And when you calculate so when we talk about the steady state current, so if I have this current that is flowing through this certain area, okay, so this is, let's say, a cross section I'm taking. So I know, because it is a steady state situation, so I know there is no accumulation of charges anywhere. Okay, so that means this J, the current density that is produced due to this flow of charges, will not or the in a way, so how any amount of charges that enter into this area, so they all will go out of this area. So there will be no accumulation of charges. So in a mathematical term, how do we say this? We say this is that the divergence of J is 0. So this is for a steady state current. Okay. So what it means that whatever charges that enter into a area, so those many charges have to, so they cross that area and go out of that. So that means a divergence of this current density L dot J is always 0 for steady state situation. But if it is not a steady state situation, so del dot J will not be equal to 0, and but it will be related to the charge density, because we saw this J depends on the charge density as well as the velocity. So you can, and we know that charge is always conserved. Okay, so charge is always conserved. So that means you don't generate any charge or destroy it. Okay, you just move it from one point to another. And what it means that, so if I take any volume which is enclosed by a surface, so if I take any volume that is enclosed by a surface S, so the current through this will be, this enclosed surface will be, let's say, J dot ds. Okay, so this is my current that passes through this, or through the surface area, which will depend on the rate of change of charge that is inside, if I have any charges inside this volume, so which is enclosed by the surface S, so the current to the surface will be equal to J dot Ts, and a negative sign is here because I'm saying the current that is going out from the surface. So this is a derivative, time derivative of the total charge that is inside. But this total charge Q inside depends on the charge density. Okay, so that's why that means we can write the J dot ds to be equal to actually minus T rho by T rho. Okay, and or this is, we will write it as a partial derivative, in fact, so not the proper derivative, but a partial derivative of the charge density, because the charge density is a function of both space and time. So it can change as a function of space and time. So that's why I'm taking the partial derivative. And now if I use the divergence theorem in here, so I will get del dot J. This is the volume. So we are converting this surface integral to a volume integral. Okay, so let me just write down that. So with the volume that is enclosed by the surface will be equal to del rho by del T into dV. So that means the integrand, I can say they are same. So this del dot J will be equal to minus del rho by del T, or I can write it as del rho by equal to 0. So this is known as a continuity equation. Continuity equation. So what it means that if I have, I'm talking about a change of or a current density through a given surface should be, this is basically the charge conservation that we are talking about. So this indicates that if there is a current flow, so that means charge is flowing, so it will depend on the rate of change of the charge density that is enclosed by that surface. Okay, so this is basically continuity equation, which is nothing but your charge conservation. But in case of steady state, as I said earlier, so del dot J should be 0. Why? So in steady state, del dot J is 0. Why? Because this rho is independent of time. It is same everywhere, and that's why the partial derivative with respect to time, so it doesn't change, and that's why del dot J will be 0. Okay, so this is a kind of thing which we need now to build up our understanding of magnetostatics. So as I said, magnetic field will be produced due to a current or current density. And how do we find out what is the magnetic field that is produced due to a current, certain current? So this is given by this famous Biot-Savart law. Okay, so which tells us that if I have, let's say, a wire where I have certain so a current. So again, we are talking about a steady state current that passing through this wire, and now I want to find out what is the magnetic field at this point due to this wire. So the starting point is, normally you define a small element dl, okay, and first calculate what is the magnetic field at this point, this small magnetic field due to this current carrying by a small element at point P. So this is, let's say we say this is a distance This is the, let's say, R vector. Or if I take a reference point, origin somewhere here, so I can say this is my position of this length element dl prime, that is r prime, and the point P is at it's defined with the position vector r. So this distance or the vector that connects the length element dl and point P is r minus r prime, and so the magnetic field dB that is produced due to this length element will be given by the Biot-Savart law, that is mu naught by 4 pi into I dl cross r minus r prime divided by r minus r prime modulus Q. So this is the Biot-Savart law, which you can use to calculate the magnetic field that is produced due to this current carrying element dl at point P. Now, in order to calculate the total field, so you have to integrate this over the entire length of the wire. So B will be then equal to mu naught 4 pi. So we just take the integral, and as we say I, that is a steady state current, so we can take this out, and this is dl cos r minus r prime. So you integrate over the length of this wire, and then you can find out what is the magnetic field due to this current carrying wire. So one thing which you must notice is that we are taking a cross product here. Okay, so this is a dl cross product with another position vector. So this you have to be careful. So this is important. Okay, and this mu naught here that we have used, this is here known as the permeability of the space. Okay, so you can use this formula for a given length. So there are some examples given in the book, so you can try that. This is one way of calculating the magnetic field due to a current carrying wire. Now, we can use this expression and calculate our familiar mathematical expressions. For example, can we find out what is del dot B? Okay, so if you do that, so just calculate del dot B for this. So the B is defined here. So now we need to calculate del dot B. So you have to use some vector identity here. So we have basically del dot B means you have a term of del dot dl cross r minus r prime divided by r minus r prime modulus Q. So you have this kind of term. So you have to use some vector identity, so which you can take from your mathematical physics course or any other if you have done this. So this you take as A vector, this is as a B vector. So try to calculate that. One, what you will get is this del dot B will be equal to 0. Okay, so this is this second Maxwell's equation, okay, which we saw many times already, a few times at least in previous classes. So this del dot B will be equal to 0. So what it means, but if you compare it with the electrostatic field, so we have the relation del dot E is equal to rho by epsilon naught, which is not 0. So this del dot B equal to 0 means you the divergence of B is 0, which means the magnetic field is unlike electrostatic field. So magnetic field does not have any source. Okay. So what I mean by that, so in electrostatic field, so when we say electrostatic field, so I can say I have a positive charge, okay, and then I have a electric field which I draw like this. So similarly, if I take a negative charge, so the electric field will be like this. So I have a source of electric field, either one charge, positive charge, or a negative charge. But I don't have such a privilege or situation in magnetostatics. So that means I cannot have an individual magnetic charge like I am defining in electric charge. So I cannot have an individual magnetic charge as such. So that means those, if I have any charges, so they will appear in pairs. Okay, so if even if I have, let's say, a magnetic charge equivalent to a electric charge, so they will always form pair. So which basically what you call as a north and south pole, and which also you say that a magnetic monopole cannot exist. So this is what normally you know. So that means if I take, for example, a magnet, bar magnet, and I keep, I break it up, so I cannot really isolate the north and south pole. So they have to exist together. So if I break it, that means a north or south pole will appear immediately. And that also means that when you draw a magnetic field lines, so it is always, it has to start from some point, so north pole, and it should terminate at the south pole. So this is what typically you see in books. Okay, unlike in electrostatic field where you have just simple charge, like isolated charges that can exist. Okay, so this is about this del dot B is equal to 0, which again also you can write as in the integral form as B. So you use the divergence theorem, so B dot ds will be 0. Okay, and also what you can we can calculate what is the curl of B. So using the same expression of B, so we can also calculate the curl of this function. So this curl of this vector. So what you will get eventually, so doing a bit of mathematics, so which I suggest you do that, because you'll be familiar with how you can deal with integration, vector integration, and use this vector vector operator and integration you can perform. So this will be helpful in doing that. So what you will get is nothing but curl of B will be equal to mu naught J. Okay, so this is a differential form of your magnetostatics. So the del dot B is 0 and curl of B will be mu naught J. Okay, so we earlier we saw in Maxwell's equation there is another extra term, so which we are not discussing right now. But in case of magnetostatics, so this is correct. Okay, so this is also known as your Ampere's law. Okay, so this is also known as your Ampere's
Sorry, sir.
law.
I just
Yes.
want to request Tipo Moduli to switch off the microphone. It's very disturbing, sir.
Yeah, please others switch off your microphone, mute yourself. Yeah, thank you. Yeah, Tipu Mudali, please microphone एक बार mute करो. Your microphone is on. Okay. So this is nothing but your Ampere's law, which best you can use in an integral form. Okay. So Tipu, can you switch off your microphone or mute yourself? So I mean, I don't have this. I cannot mute anyone, so otherwise I would have done that.
Okay, sir, you continue. Yes,
Okay,
please.
so this Ampere's law you can use uh, in the integral form, so which is much more easier, in fact, to calculate the magnetic field due to a current density or any current. Okay, so how do you do that? So here, what you do is you use again like what we did for electrostatic case. So here we will take the uh, a surface integral of both sides. So I will take a curl of B uh, dot ds. So you have to be always careful about this vector sign and whether you should use a curl or a dot product or whatever you are going to use. So be careful of that, because many times people do a lot of mistakes, where to put a vector sign, where not to put a vector sign, whether to put a make a dot product or cross product. Okay, so this you should do carefully. Okay, so this will be again on the right hand side. I'm again taking a surface integral. Okay, so this is the surface integral. And this surface integral on the right hand side is nothing but is the number or the total current. So J dot ds, the integral over J dot ds is nothing but the total current that is enclosed within a, a line that bounds the surface. Okay, so this is a current that is enclosed uh, within the length or the line that encloses or makes the surface. Okay, so this is similar to what you have seen in electrostatics as well. So when you are using the Gauss's law. Now, what is the left hand side? So left hand side here you will use. So this is a del cross b dot ds, which we can convert to a line integral. So which you use the Stokes theorem. And what you will get is this b dot dl over the closed closed path, the path that bounds the surface basically. So this b dot dl will be simply be equal to I mu R enclosed. So this is another integral form of your Ampere's law, which many a times you will use, or it is easy to use to calculate the magnetic field due to a certain current, if you have a flow of current or flow of charges. Okay. So this is similar to your Gauss's law in electrostatics. So you can take some examples from the book and try to solve that. Uh, so what you can already realize that we are seeing some amount of similarity between electrostatics and magnetostatics, although they are not exactly same, but some similarity that exists between electrostatic and magnetostatic. So then can we thought of like we defined in case of electrostatic, we define something as a electrostatic potential, because we started with the force, okay? Then we say Coulomb force, then we said, oh, this is how we can define the electric field, okay? And for a given charge distribution, we can calculate the electric field, so we can use a Gauss's law. So here we have developed, so we have the magnetostatics where we have a steady state current, and that can produce a magnetic field, which we can calculate using Ampere's law. But then we said, this since electric field is conservative in nature, so we can now express electric field as a gradient of a potential, okay? And this scalar potential is formulation is useful because now for a charge distribution, to find a scalar function is easier compared to a vector function, always, because in a vector function you have always three variables, but in a scalar function it's only one variable, or so there is no direction dependent, so it is always easy to calculate a scalar function. So that's why we defined the potential, so we can calculate the potential for a charge distribution and use Poisson's equation or Laplace's equation and calculate V, and then eventually we can calculate electric field. Can we do something similar here? Here it is not easy because already what we saw is that we don't have this exact equivalent of Gauss's law, okay, which, or this magnetic field is not like a conservative, like what we saw in case of electrostatic field. But what we can do is we can write something as, since we have this del dot B is 0, so we know that the divergence of, if I take a divergence of the curl of a vector, so it will be always 0. Okay, so if I take a divergence of curl of any vector, so I take a curl of any vector and take the divergence of that, so this is always 0. So this is simply, I'm just writing divergence of curl of A. So A is, and again, it has to be a vector, so it is always 0. So that means I can define or write my B field as a curl of A, and this A is known as a vector potential. Okay, so it is not a scalar electrostatic scalar potential like we saw earlier, but it is a vector potential. Although, if you look carefully, so this vector potential really does not have any physical meaning or existence as such, but it is useful in many cases to solve problems in electrodynamics, particularly when we talk about time varying magnetic field. So it is very useful to use a vector potential. So that's why you need to know a little bit about what is a vector potential and how that can be used to calculate. So simple relation B is equal to curl of A. Now the choice of A, so what should be A, can be actually arbitrary. Why? So if I take, let's say, define A as a, or a new vector, let's say, I define A plus gradient of a scalar. Okay, so let me define a vector like this, and if I take the curl of this vector, so what I will get, this is curl of A plus curl of this gradient. So psi is a scalar function. So this will be, now if I take the curl of a gradient, so this is 0. So this is again another identity that you should always remember. So curl of gradient of a scalar is always 0. This also you can prove actually. So in mathematical physics, if you haven't done that, you can try to also just use it and calculate what is the curl of a gradient, the divergence of a curl. So all those you can calculate and prove this identity. So this is nothing but simply curl of A, so which is equal to B. So that means this choice of a vector potential can be arbitrary. So if I just add a gradient scalar, gradient of a scalar, so I can get produce the same magnetic field. So the vector potential is different, but the magnetic field that is produced is the same. So this kind of situation is quite useful when we go into electrodynamics in the future. Okay, so in a way, but if you look at this vector potential, it has a form of something similar to a linear momentum. Okay, so in terms of its dimension, it will have the dimension of similar to a linear momentum, but it does not represent the linear momentum of your charged particle or anything else. It is actually some arbitrary a potential or function, even it is not a real potential. Okay, like in electrostatic, you have a real potential, which in fact you can measure, or the potential difference you can measure, right? In capacitor, for example, or using a voltmeter. So you can actually measure the potential difference in case of electrostatic, but you cannot do any measurement of vector potential. But it is a useful mathematical tool which helps in electrodynamics. Okay, so there will be some mathematics also associated with that, which you can look it up into in the book. Okay, so the next thing which we will talk in terms of magnetic field. So what we have seen is, sorry, so what we have seen is, so similar to electrostatic. So we have electrostatic is del dot E equal to 0 and curl of E is at 0. So everything we are talking about electrostatic. So similarly, we have a magnetostatic where del dot B is 0 and curl of B is equal to mu naught into C. Okay. So this is basically in one case we are talking about stationary charges, and in the other case we are talking about the steady state current. So in magnetism or magnetostatics, when we talk of magnetostatics, there is another interesting quantity that appears quite often, because particularly of this condition, this del dot B equal to 0. As we said, the isolated magnetic charge cannot exist. So that means whenever we say there is a magnetic field, it is produced not due to a magnetic monopole, but due to a magnetic dipole. Okay, so always a magnetic field will be always associated with a magnetic dipole. Okay, so this dipole will be related to your magnetic field B as well as your vector potential A. Which like you define as, it is again a vector M or mu sometimes. Okay, so people use different symbols to represent this magnetic dipole. And what this dipole is like, if I have a north and south pole like a bar magnet, so this is my produces a magnetic dipole, for example. And this will also have a corresponding magnetic field, and which you have seen quite often in your school and other. I mean, you are familiar with this. Okay, so one can calculate, in fact, or find a relation between this B and a dipole moment. Okay, so which is, I will just simply write down the formula without deriving it. So the magnetic field produced due to a dipole, a magnetic dipole, is given by mu naught divided by 4 pi m by r cube, or we write down in this form. So 1 by r cube into 3 m dot r minus m. Okay, so this is again a relation between a dipole moment, magnetic dipole moment, and the magnetic field that is produced due to this magnetic moment m at a distance, at a position, at a point r here. Okay. So there is similarly also you can use in case of electric dipole. So one can also find out what is the electric field due to a electric dipole, which will be this constant 1 by r cube. So a similar expression also exists. So by nature they look pretty similar, as you can see. So only you replace m by the dipole, electric dipole moment p. Otherwise the expression look exactly the same. So this is how you can produce a magnetic field due to a magnetic dipole or electric field due to an electric dipole. Okay, so so in magnetism, always, so one important problem you should get used to is something known as solenoid. Okay, so there is something known as solenoid. So please look it up in the material that is shared with you. So you should be able to calculate what is the magnetic field produced due to a solenoid. So what is a solenoid? It is nothing but you take these coils, okay, so current carrying wires. So you take these current carrying wires. So you wouldn't set coils around a in this. So you can take any. So it can be a piece of wood, or it can be metal, or any other material, for example. So you just wound these coils, or even in free space, if you wound it, this kind of coil. So what you create is a very uniform magnetic field. So the solenoid is used quite often in many uh, physical situations to produce magnetic field. And this is where you should be able to calculate what is the magnetic field. So you can use just simply the Ampere's law to calculate what is the magnetic field that is produced due to one single current carrying wire, and then you can extend it to these coils and find out what is the magnetic field that is produced due to this the solenoid kind of geometry, which is always interesting in many physics experiments. So please go through that. So before we move on, any question? If you have any questions so far, so we'll take
Sir,
it.
solenoid is in which chapter of our material?
It is in chapter 6 of this magnetostatics.
Okay.
So the online material that you have, or the PDF you have, so it is in chapter
Huh.
unit 6. So you
Let's say
look at block
pa-
block 2 of this course. This is 3, okay, MPH-3, block 2.
page number, sir.
Page number solenoid is one. I have to see. I think around 170, 374. Yeah, 173, 74, and 75. Yeah, 175.
Okay, sir.
Okay. So mostly, if you are able to just calculate what is the magnetic field due to this solenoid, that is good enough. So you sometimes you would hear in the book, I think also they have used this vector potential notation, but it is not really necessary. So you can simply use the Ampere's law and calculate this magnetic field, because it is just simply a cylindrical symmetry. Okay. So you want share Google Classroom? Give a moment. Google Classroom.
Excuse me, sir. Sir,
Yes.
one term is given Coulomb gauge.
Yes.
Can you explain its physical importance, please?
So there is
On
no physical meaning of a Coulomb gauge. So what
on
when we
161.
talked about this vector potential, no? Okay, so we defined this vector potential. We said it can be arbitrary. So this vector potential that can be used to produce a magnetic. So let's say we want to produce a magnetic field B. Okay, so of course you need to flow a current and you produce this magnetic field B. But for mathematical convenience, so since we have something like a scalar potential, so then also a concept of this vector potential was introduced. Okay, and it was used again. This vector potential can be used to represent the magnetic field, because you can calculate if you know vector potential and take curl of that, so you say you get a magnetic field. But what you see is this vector potential is not uniquely defined. I mean, if you look at scalar potential, also it is not uniquely defined. Okay, so if I say my scalar potential at any position r is v, but always I have to calculate it in terms of some reference point. Okay, now if I change that reference point, so let me say what I mean. So let's say I want to calculate, so I have certain charge distribution and I want to calculate what is the potential at this point P. Okay. And so how do I calculate? So I say this is, I have taken a reference here. Okay. And now I am calculating what is the potential at V with respect to uh, this reference point O. Now, if I shift this reference point O prime to another, for example, so this V, what would happen to V? So it will be VR plus some constant. Okay, so you just add some constant term. So relatively, like, uh, and okay, so now if I want to calculate the electric field, so which I say it is a gradient of V. Now, if I take the gradient, so let's say I define a new function VR. So this is again, if I take a gradient of V prime, so it is simply gradient of V, because if I have any constant term, so the gradient will be 0. So this is similar thing we are talking here also. So we have defined a vector potential A, and if I take the curl of this vector potential, I will get B. But I can take another vector potential, which is now differing by a certain value. So, but that value is the gradient of another scalar and some scalar. That will give me the same B also. Okay. So now let's take the curl of, but we know that del dot B is 0. Oh, sorry. So let's calculate what is the curl of this. So we know curl of B is equal to mu naught J. And now if I calculate the curl of the left hand side, so this is curl of A, which again you use a vector identity, which will tell you this. So it will be del into del dot A minus del square A del square A. Okay, so in case of electrostatic, what we could do, because it is a scalar function, so what we could do is we could write an equation like del square V is equal to minus rho by epsilon naught. That is your Poisson's equation. But in this case, we have a difficulty because we have two terms, del dot A and del square A term. So in order to write, but we can choose our vector potential A. So because it is, the choice is with us. Okay, so what should be the vector potential which give rise to this magnetic field B, since it is arbitrary. So we can, it depends on us, like how we choose the vector potential, and we can choose a vector potential such that del dot A is 0. So this is our choice. Okay, so this you can actually construct. Okay, so you can construct a vector potential, so which because it is just, again, it is a vector. Okay, so you create a vector which satisfies both conditions, del dot A equal to 0, and if I take now curl of A, it should be also equal to B. Okay, so this condition or the choice that we have made is in electrodynamics, it is known as a, this particular situation, del dot A equal to 0 is known as Coulomb gauge. Okay, so that is the name that is given. So your choice of the vector potential is such that del dot A will be 0, and that's why we can then write down this or simplify this Ampere's law in terms of a vector potential. I can write it as minus, so it will be equal to minus mu naught J. Del square A will be equal to minus mu naught J. So this is similar to your electrostatic potential, where we defined a Poisson's equation. So here also we are writing a similar equation. That's all. So this gauge name of the gauge is pretty much not related to really classical electromagnetism, but it is useful when we go into electrodynamics or field theory in physics. Okay, so there the gauge represents some kind of a symmetry. Okay, so we will talk about the symmetry, and so may not be really detail into the gauge conditions and theory, but this is useful when you go from classical electrodynamics to transition into a quantum electrodynamics. Okay, or quantum, like when you want to use a quantum electrodynamics, there this gauge concept will be needed. Okay.
Thank you, sir.
Okay, so So now, uh, so the classroom link I will share. Give me a moment. Okay, so this is the classroom I have shared now. So if anyone has not joined yet, so please join. Okay, so the next thing what we are going to discuss is like how magnetism uh, is it appears in different in material system. Okay, so like what we saw in the last class in case of electrostatic. So when we talk about dielectric material, so if I take a conductor, the electric field will be zero inside it. Okay. Now, if I take a dielectric, so the electric field is not zero because there will be some bound charges that appear within the dielectric material, and that leads to a polarization of the dielectric material. Okay, so polarization, which you can then write down a different kind of vector, this vector displacement, uh, this electric displacement vector, which we define as this vector D. Okay, so which is nothing but your depends on the polarization. So it is a vector sum of your electric field and polarization. So similar thing will also happen if we put any material in presence of an external magnetic field. Okay, so let's see what can happen. And but only thing is in magnetic when we talk of a magnetic field, so we know we cannot create any isolated magnetic charges or monopoles. They cannot exist. So whatever will happen in the form of magnetic dipoles. Okay, so uh, uh, so if you think of, let's say, an and this is very interesting, like I mean people have tried, so just to add on this magnetic monopole thing, because people still believe that one can find magnetic isolated magnetic charges or magnetic monopole in nature. So there is still experiment going on. People are still trying to do research on that. So it is not as if it is well established that magnetic monopole cannot exist. It may exist. So people are still trying to experimentally find it out in nature. So far, we haven't found it. Uh, and even I mean that what it means, like even if I go to an electron, which is a point particle, and we say electron also has a dipole moment. Okay, it has a magnetic moment, and it is due to a dipole. It is like similar to a dipole. Okay, even we talk about elementary particles, so electron, even we talk of neutrons, protons, they all have magnetic moment, and this is all like a dipole moment. So even in an elementary particle system, we have not yet found any magnetic monopole yet. But the search is still going on, and if we find, so we have to definitely modify or change our Maxwell's equation. Okay, so uh, I think the most familiar thing which in magnetism is like if I put any magnetic material close to a magnet, okay, so if it gets attracted, we say it is a magnetic material. If it does not, so we say it is a non-magnetic material. So this is a simple way of saying the difference between a magnetic and non-magnetic material. So which is, let's say, magnetic material, for example, iron or cobalt or nickel, it will get attracted when you put it close to a magnet. But if you take a rubber or wood or plastic, so they will not really get attracted. So they are non-magnetic. uh, like what we said in case of dielectrics as but what is the origin of this kind of behavior? So in one case we can say we have some magnetic dipole, permanent magnet dipole that exists, but in other cases the question is, can we have similar to like induced electric dipole, like we had an induced electric dipole in case of dielectric or a non-polar material? So can we have an induced magnetic moment in non-magnetic material? Okay, so we say we have two kinds of materials. One is, so we say is a non-magnetic, and there is a magnetic material. And now non-magnetic is not attracted by the magnet. So can we have a induced magnetic dipole here? And what will be the form or nature of that? And of course, magnetic material will have a permanent dipole moment. So without any applying any magnetic field. So based on this induced dipole moment, so you can have a material known as a diamagnet and a paramagnet. Okay, so this is again, you are familiar with this picture. So if I have a diamagnet and I apply a magnetic field, so the magnetic moment M or the dipole moment M will be opposite to this applied magnetic field. So similarly, if I take a paramagnet and I apply a magnetic field, so the induced dipole moment will be along or applied parallel to the magnetic field. So this is kind of a situation which also you are familiar with. So this is a diamagnet and paramagnet. So diamagnet example is water, for example, is a diamagnetic material. Okay. And paramagnet example will be aluminium, or you take for example, liquid oxygen. Okay, so this is paramagnet. But most of the metal that we think of are mostly paramagnetic in nature, except copper. Copper is a diamagnet actually. Okay. Mm, but most of the material actually, in a sense, are paramagnet in nature. And out of that, like iron, cobalt, and nickel typically are most famous ferromagnetic materials. So the question is now, why these materials behave like that? Uh, so you can think of in terms, so what we will use mostly a classical understanding of this. So there is definitely a much better understanding is a quantum mechanics will give a better explanation why materials are diamagnet or paramagnet or ferromagnet. But we can understand using also classical or semi-classical arguments or understanding, and find out why materials behave in a certain way in this form. Okay, so one thing which is also interesting, uh, when you look at a magnetic field due to a bar magnet, so this is N and S. So this is the magnetic field due to a bar magnet. Okay. And if I take a circular loop where I have a current, okay, and the magnetic field produced due to this current carrying wire also is very similar. Okay, so this is, let's say, the magnetic field that is produced. So if the current is flowing clockwise or anti-clockwise direction, so let's say the current is like this. So the magnetic field lines all will be like this. Okay. So this is very similar in nature when you look at the kind of magnetic field that is produced. And that's why when we think of atomic systems, okay, and this is what actually led to this realization, at least from a classical picture, that atoms can also have a magnetic moment. Why? Because the atoms are similar to, like, you think of there is a nucleus and then the electron is orbiting around it. So an electron orbiting around is similar to like a charged particle that is moving across in a circular, let's say, if we assume it is a circular path, although we know this is not correct, but a classical picture would be that a electron is moving in a circular orbit around, so the Bohr orbit, it is moving around the nucleus. So it is similar to a current that is carried in a circular ring, and that's where it was realized that yes, atoms can also have a magnetic moment. Although the better explanation that we have right now from quantum mechanics is because you have an orbital angular momentum and a spin angular momentum, so that gives rise to the magnetic moment in an atom. Okay. Mm. So this origin of a magnetic moment, the atomic or existence of magnetic moment or dipole moment in atom is actually responsible for a material to behave as a ferromagnet or a paramagnet or a diamagnet. Okay, so this all this tiny magnetic dipole moment that is associated with the atom that is responsible for your material to behave in certain way. So in a classical, since we still want to keep things simple, so in a classical picture, as I said, I have a nucleus. Okay, so electron is orbiting around it. Now, if I say this is equivalent to a current, this electron that is going around this nucleus will produce a current which is E by T, or this is the time period for the electron to take one orbit, which will, but what will be the value of this T? So if the electron has a velocity v, okay, so now in time t, or if this is the time period for one electron to complete one orbit around the nucleus, so I can write the 2 pi r, so which is the radius of the electron from, or the distance of the electron from the nucleus. So that is the radius of the circle. 2 pi r will be equal to v into t, and t will be simply equal to 2 pi r by v. And so current will be simply given by, so here, since we are talking about electrons, so we will take a negative charge. So this is minus E by T. So this will be minus E V by 2 pi. Now, what is the magnetic moment that is produced due to this kind of circular motion? So if I have a current, so if I have a wire, okay, with a current I, so the magnetic moment is simply is equal to I into the area. So this is the area of this circular path. So which is nothing but is pi r square. So this is the magnetic moment that is produced due to this current. Okay, so which is now due to the electron. So now we can substitute in place of I. So we know what is the expression for I. So we can write M will be equal to minus E V, the 2 pi r into pi r square, which if I simplify, so it will be V V R by 2. Yeah, that's all. So pi will cancel out, 1 r will cancel out, so it will be minus V V R by 2. But we know what we are talking about is a model of electron, atomic model of electron. So in that case, we also know that this orbiting electron has an angular momentum, so orbital angular momentum. So this orbital angular momentum is nothing but r cross p, that is the linear momentum. And in this circular orbit, so we can say this is equal to m, the mass of the electron, so r into v, simply. So the momentum is me into v, and the momentum is always perpendicular. So due to the velocity is always perpendicular to the r vector. So r cross p. So the angle will be always 90 degree. So this is simply me r into v. So we can then write the magnetic moment in terms of the orbital angular momentum, because we have defined, so this is EBR by 2. So I can write now this magnetic moment as in terms of this L, which will be equal to E minus E by 2 ME. So in place of VR, so I can simply write VR is equal to L by ME. So this is, I can write this magnetic moment is equal to minus E by 2 ME into L. So this is why we always say that the magnetic moment, the dipole moment of electron is always opposite to this orbital angular momentum, this L. So this is due to this negative sign. Okay, so this ratio of this magnetic moment to this orbital angular momentum, this m by L, is also known as gyromagnetic ratio, which is a constant. So if I look at this m by L, so it is a constant. So only E and ME are there. So this is known as gyromagnetic ratio. Okay. And in fact, you can also express this magnetic moment in a more fundamental way, which is known as your Bohr, your Bohr magneton. Yes. So also, if I use the Bohr's postulate, so I can write L is always will be quantized. So your uh, orbital angular momentum is always quantized in h cross term. So it is nh cross, or this is like, or simply you just write nh by 2 pi. Okay. So if you substitute this L in magnetic moment, so you can calculate even what will be the magnetic moment, the fundamental unit of a magnetic moment of an electron, so E by 2 me. So it will be just h cross by 2 me. So this is known as your Bohr magnet. So you can calculate, these are all fundamental constants, which you can substitute and find out what will be the value of m, which is known as a one Bohr magneton. So sometimes for electrons, we say that the magnetic moment it carries is one Bohr magneton. So this is normally also represented in a symbol mu b. Okay. But also it was realized it is not only depends on L, the orbital angular momentum, also it depends on the spin. Okay. So classically there is no such analogous term we can get. So this has to be introduced empirically or arbitrarily, the spin. Of course, the exact origin, why the spin is there and how the spin can lead to a magnetic moment, all can be done in quantum mechanics and advanced quantum mechanics. But simply in this case, so we can say also this magnetic moment can also have a dependent on spin, which is the related to the spin angular momentum, and this is the relation. Okay, so uh, this is which is the spin, which is the intrinsic angular momentum, which does not have any classical analog. So that can also lead to a magnetic moment of the electron. So even that means electron which is free, which is not bound to atom, which does not have any orbital angular momentum, can still carry a magnetic moment. Okay. So this is about the magnetic moment of one electron. But in an atom, you have many electrons. And when we talk of a material, there are many electrons. So you basically have to add of all these magnetic moments. So if we say this is all just a vector, you just have to add them, and then you get the total magnetic moment. And then you can define a term which is known as magnetization. And what will be the value of a magnetization of a material? So this is the dipole moment, all the dipole moment uh, per unit volume. So you find out the summation of all the magnetic moments that you, the atomic magnetic moments, and you divide by the total volume, so you'll get the magnetization, which typically one can experimentally measure. Okay, uh, so one can understand based on this magnetic moment, one can understand what is the origin of diamagnetism, paramagnetism, and ferromagnetism. So diamagnetism, as I said, is due to the or what it means that if you are applying a, so if I take, so if I take a material and I apply magnetic field B, so I will induce these dipoles. So these are all represents, let's say, this tiny magnetic moment M, dipole moment M. So they will be induced in opposite to the magnetic field B. So they basically what they are trying to do is they are trying to oppose the field that is responsible for this. Okay. So this is kind of a similar to Lenz's law in classical physics, you say. But the deeper understanding, so one can also get why this happens from a semi-classical understanding. So one approach we will take here So in the book, you will see the two approaches have been taken. So you can choose any of the approach to explain why diamagnetism is there. So if I take, let's say, so we will just quickly do that. So I have a electron. So this is my nucleus. This is the electron. This is the electron orbit. Okay. So this is my vector r, or the position, the distance, the radius of that orbit, and I have this velocity v, this electron that is going around the nucleus. Now, when you look at the forces here, so just from a classical picture, so you can say what are the forces acting here. So one is the centripetal force, and the other is the Coulomb force, that is the attraction between the nucleus and the electron, which is the electrostatic force. So assuming this is a hydrogen, so Z will be equal to 1. So this is a proton with a positive charge, and you have electron negative charge. So this will be E square divided by 4 pi epsilon naught R square by R. Oh, this will be, yeah, R square. So this is the force, so Q1, Q2 by R square. Okay. Now, if I have a magnetic field, so now if I have now applying a magnetic field here, so what happens? So there will be another additional force, that is the Lorentz force, that is acting on the electron. So this Lorentz force, so I have the same orbit. Okay, so the orbit is still maintained due to the centripetal force, but I have, in addition to the Coulomb force, so I have a additional force, that is the Lorentz force. Okay, and this V1, which is the change in velocity. So this V1, this is a modified velocity due to the magnetic field. Okay, so this is the additional force we have. Now we have two different velocities we are writing. So one is here MeV square by R, another is this velocity. Okay, so and we are saying both are kind of perpendicular to the magnetic field as well. So we can rearrange now this. So we have one equation here, MeV square by R is equal to this much, and also we have this kind of equation here in presence of a magnetic field. So if we substitute this this equation here, okay, so we can now write down that our EV1B will be equal to ME divided by R. So this is a V square minus V1 square. Okay, so I should write here as V1 here. So we have initially without a magnetic field, so we have this kind of equation. So now due to the magnetic field B, so the velocity is modified, although the orbit is not changed. The orbit is still circular. We are keeping that like that. So there is a change in velocity, MeV1 square by R. So which will be, so this equation comes from that. So now substitute this. So in place of 1 by 4 pi epsilon naught, so I just substitute this equation here. So I will get this kind of relation. So which we can write as V square, or just write as V minus V1 into V plus V1. And assuming that this change is very small, okay, so this delta V here. So this delta V is very small. So we can write down this as ME by R into 2 into V into delta V. So we are assuming this change is small. So that's why this V and V1, when we are adding, so they will just give rise to this 2V term, and the difference will be the delta V term. Okay, so if you do that, so we can now, it can be 2V or 2V1. So this way you can cancel out this V on both sides, V1 from the both sides. So the change in the velocity we can write as EBR divided by 2m. Okay, so this is the change in velocity due to this magnetic field B. And also what we know that this change in velocity or change in speed will lead to a change in the magnetic moment. Why? Because we already know that we saw earlier that our magnetic moment is, which is basically proportional to your orbital angular momentum. So we can write it as minus EBR by 2. So this is the magnetic moment, which is always proportional to the velocity of the electron. So if we use this equation here, so what we will get is delta or the change in magnetic moment, delta M, due to this change in the velocity delta V will be given by minus half E delta V into R. So this is due to the magnetic field, there is a change in magnetic moment, the dipole moment delta M, which is given by this. And now if I substitute all those terms, so delta V we have calculated this. Now I substitute here. So what I will get is equal to minus half E. So then E B R divided by 2ME into R, so which gives rise to E square B R square divided by 4ME. So this R square that we are writing, one can also write it in terms of the average or the expectation value of this radius, which also one can express sometimes in terms of the Bohr radius as well. Okay. But whatever form, now what we see here, this delta M that is induced, so this is the induced dipole moment, it is negative. Okay, so this is what we see already, it is negative, and it is also proportional to the magnetic field B. Okay, so that means the higher the magnetic field or the more, if we increase the magnitude of that magnetic field B, so this delta M, the induced dipole, will be much larger, but it will be always opposite in direction to this applied magnetic field B. So this is the origin, one way of explaining how diamagnetism arises in material. So just to summarize all this mathematics that we have done, so what we are saying is when you have an orbit and you are applying a magnetic field, so this orbit or the electron velocity is going to change because of additional forces, for example here Lorentz forces, and that will lead to a change, but again the orbit, so electron want to be in the same orbit, so it resists that change. And in order to resist that change, so how it responds, so it develops a dipole moment, induces a dipole moment that is opposite to this external field B, and that is what the diamagnetism is, and that is why we say it is always opposite to the applied external field. Okay, so this is, there can be also other explanation also, but this is again a semi-classical thing which we are talking about. Now another, so this is about diamagnet. The next material that is interesting is a paramagnetic material. So what happens to paramagnets? So paramagnets is a system where what happens is you have the magnetic moment in the same direction as the applied magnetic field. So where this dipole moment comes from, so this is again most likely you have lots of unpaired electron that exist. Okay, so if you have unpaired electron in the atom, so that would give rise to this dipole moment, which will always exist. But let's say they will exist in such a way that they will all be in a random orientation. Okay, so this is when I'm saying B is equal to 0. But as soon as I apply a magnetic field B, which is not 0, so these dipole moments will orient along this magnetic field direction, and you get this a paramagnetic behavior. Okay, so when how do they orient? So that means there is always a torque that acts on this dipole moments. Okay, so this torque leads to this orientation of the dipole towards the magnetic field. So what is this torque? So this torque is actually a cross product of your magnetic moment with the magnetic field. Okay, so this is the torque that acts on the dipoles, and that makes sure that the dipole moments get aligned along the magnetic field. But this torque does not, it is not like it will just bring the dipole moment instantaneously to align along the magnetic field. But what it does is the magnetic moment, typically because it is associated with the angular momentum, it is always will precess first around the magnetic field. So what do I mean? What I mean by precess? So if I have a magnetic field B and I have a dipole, magnetic dipole like this, so it will start precessing around the magnetic field B, and then eventually it will get aligned along the magnetic field B. So this precession, so this is has a special name, precession. So it is because the magnetic moment is associated with angular momentum. Okay, so it just like a vector which will not just flip and get aligned along the magnetic field, but it will move around this magnetic field. So it will move, recess around it, and then slowly it will align along the magnetic field. Okay, so it will recess and then align along the magnetic field. So the precessional motion, it occurs at a certain frequency. Okay, so this is of course will be related to what is the angular momentum, as I said. So the total angular momentum, it is not just simply the orbital or spin, it will be due to the total angular momentum of the electron. And the precessional motion, the frequency of precession is equal to, given by this again some fundamental units, E by 2 me into B. Okay, so this is known as Larmor precision. Okay, so as you can see, the stronger the magnetic field be, so the frequency, Larmor precession frequency will be large, and for a small field, so this frequency will be small. So it starts precessing, and then eventually it will get aligned along the magnetic field. Okay, so one thing which also we should emphasize here in case of this paramagnetism. So the magnetic moment that we are talking about is dipoles. When we are saying they are randomly oriented. So why they are randomly oriented to start with? This is because of a thermal uh, so you can say this is due to the uh, temperature or the thermal effect. Okay, so due to temperature, the magnetic moments always will be randomly oriented. Okay, so what it does that that means the magnetic moment. So when we talk of a magnetic average magnetic moment of a paramagnet, so that is of course will be always directly proportional to the magnetic field B, but it will be inversely proportional to temperature T. Why? So this is the average magnetization or magnetic moment of a paramagnet. Because as you can see, if I apply a more magnetic field B, so all the dipoles will align. So my average magnetic moment along the field direction will be maximum. But now if I increase the temperature, so this dipole moments will fluctuate even faster, and that's why the average magnetic moment will be smaller. So that's why it is inversely proportional to T. Okay. Uh, and then the interesting material that we have is the ferromagnet. So where we have a permanent dipole moment. So you have a permanent dipole moment, but not only that, of course, you have a permanent dipole moment in paramagnet as well. But what is interesting here that these dipole moments they interact in such a way that they are aligned and they don't need any external field to get aligned. Okay, so they will always align spontaneously. So this is a spontaneous alignment of dipoles. So how this then can be demonstrated in a ferromagnetic material? So this, what we call, they form these regions which are known as domains. Okay, so what you form is known as domains. And what are these domains? So when you look at just one domain, so within one domain you have many these tiny dipole moments which are all pointing in the same direction. Okay, and this is what we represent by this big arrow. So there are all the small dipole moments due to your which are of the atomic in origin or due to spins. So they will all point in the same direction within this region. So that is your domains. Uh, this is interesting. Why this happens? This is again there is no classical explanation. So what the the origin here? Why they are all within this domain? Why they are all pointing in the same direction? So this is known as due to the exchange. This is a quantum mechanical interaction. So exchange interaction or exchange force. In books also you'll find this name also. So this is due to the exchange interaction. So we are not going into what is the origin of this exchange, but simply just so that you know or you are aware of this. So the domains they form due to this exchange interaction. Okay, so what happens when you are applying a magnetic field here in this case? So the thing is, which also you are familiar with. So if I apply a magnetic field to a ferromagnet and I look at what is the magnetization, so what I see is a hysteresis. Okay, so this is a very unique feature of ferromagnetic material. So you have a hysteresis. So that means the magnetization value depends on the history. Okay. So where you were, depending on that, so the magnetization value will change. But nevertheless, this is a like a signature of a ferromagnetic material. So similar to a ferromagnet, so you have also materials which are antiferromagnet or ferrimagnet. Okay, so we will not go into the detail of that because with the limited scope here, we cannot really explain what is the origin for that. But one thing which is interesting when we think of in terms of the magnetic materials, uh, if I take so if I take, let's say, a big arbitrarily shaped magnetic material, and I say this is uniformly magnetized. So what I mean by that, so all the atomic moments, they are pointing in the same direction. Okay. Now, in a classical picture, so what we say, what is the origin of this? We say it is due to this all small orbits. Okay. So these tiny electrons which are going around, or like the current. So we said this is the electron which similar to, you can represent it like a current loop. Okay. So we are representing it as a current loop everywhere we have, which give rise to this magnetic, like this situation where all the magnetic moments are pointing in the same direction. But if you look at a little bit closely here, so two neighboring loops. So what you see here, that the current here, so let's just look at this section here. Okay. So the current is flowing in this direction here, clockwise, and here it is anti-clockwise in this. And assuming they have all the same magnetic moment, so we say, okay, the current will be the same. So, but that means they will cancel each other out. And what would happen? So only you have currents only at the edges. So you have currents only at the edge that will exist. It will all cancel each other out within the block or within this magnetized material. So you have a classical situation where the current that is only going along the boundary that that keeps, or the boundary of the material. Okay, so this is a situation, a classical picture of this uniformly magnetized medium. Okay, so okay, so we are already close to the. Any questions so far? Any question?
No, sir.
Fine. Okay. So what I want to then just complete our discussion for today. So this is like how you can distinguish between a magnetic material when you are applying a external magnetic field. Uh, but when we think of the, let's say when we talked about dielectrics, so we said due to the electric field, so we have something known as uh, so now what will be the situation or how this magnetic field can be expressed uh, and how it is related. So we have a magnetic field B, and we have something known as we are calling as a magnetization, which is we define as the magnetic moment per unit volume. Uh, and so how do we now correlate these two quantities? So we have some quantity B and M. So for a material, so how do we find what is the relation between these two? So this we can realize. So let's say again, let's write down this equation, the Maxwell's equation that we wrote. So curl of B, we said it is mu naught J. Okay. Now, in case of a material, so we can, and this B, magnetic field B, now we say it can be produced due to, so if I have, let's say, a wire which carries some current I, which corresponds to a current density J, so that will produce a magnetic field B. But also, I can get this magnetic field B without any current, without flowing any current, but just purely due to this atomic magnetic moments. So if I have this dipole moment, so I can, which comes from this atomic, the electron orbital motion and the spin angular momentum, it can give rise to a act similar to a current loop, and that can give rise to also a magnetic field B. So this J here, which I am writing as a J total, I can write this as a J free plus a J M, which where M it indicates it is due to this atomic dipole moments. Okay, so you have the total current density can be, so why I am writing it like that? So I am saying that this magnetic field B is always due to this produced due to some current density. Okay, so now, but I know now this magnetic field I can produce. Of course, if I have a current carrying wire, so it can produce a magnetic field B. That is clear. But within a material, I can produce this field also due to this atomic motion, okay, or the electron motion. The orbits, because simply they have a orbital and spin angular momentum, they can also produce a magnetic field. So how do I then incorporate this information into this Ampere's law right now? So in that case, so I will write actually J, that is the total current density. So this is a free current density. Of course, I take any wire due to that. But also, if I have a material, so I will have this dipole moments, which can give rise to a current density as well, similar to a current loop that we saw right now. And that can give rise to a magnetic field as well. So that's why my Maxwell's, the Ampere's law will be modified, and I am writing as J3 plus Jm. And again, so this Jm, the origin is, this is due to the atomic motion. Can we measure it? Not easy. Okay. Again, there are ways you can do that, but it is not straightforward because you cannot really measure individual atomic moment and say how they are arranged. You just add up vectorially, so it is not easy. But still, we can think of there is a contribution from that. And now we can write it something like, so I just write it to separate terms, mu 0 Jm. And this Jm, we say this is a similar to a like in dielectrics we saw there is a bound charges. So this is what we can call as a bound current. Okay, so this Jm we can give a name, and we say this is a bound current. Okay, due to magnetization. And how it is related to our magnetization M. So this is equal to a curl of this magnetization M. So why we are saying that? This is a curl of this magnetization. So when you look at this loop that we have drawn here, so what we are saying is like the magnetization is due to, let's say, the magnetization that is produced in this material is due to a current that is flowing on this boundary. Okay, so that means if I take a curl of this current density, so this is like a curl kind of situation. Okay, so I'm moving the current around the boundary. So if I take the curl of this current density, so that will produce my magnetization. Sorry, if I take the curl of this magnetization, so that will give rise to my current density M. So there is two vector quantities we want to correlate, or we want to find a relation between them. So one is magnetization. So this magnetization is, so if I say this is in the plane, so I would say always the magnetization will be in this direction. So this vector, how it is related to a vector which is on the surface. So this is basically a curling of this M vector, which gives rise to my current density J on the boundary. Okay, so this is without, I mean, one can also mathematically kind of prove this relation that I am writing. So Jm is equal to curl of M, which also kind of indicates that your this so the curl. Okay, so if you look at the curl of this vector M, so it is a kind of a discontinuous at the boundary. Okay, because it is non-zero, so M is zero outside, of course, but it is not zero inside this boundary, and this gives rise to a discontinuous change in the magnetization. And this is expressed here in a, so if you take the curl of this M, so you get the bound current due to this magnetization. Okay, so that means if I take any material where there is no such dipole moment or no magnetization, so of course, or if I take something which has a uniform magnetization, so in that case, this Jm will be equal to 0. Or M is constant everywhere. If I say M is constant everywhere, so it will be 0. But in the material, so M is not always constant, so there is a change. And also, so that gives rise to this bound current due to the magnetization. Now, that I can now write down this curl of B as mu naught J free plus mu naught curl of M. And so I can now write B, so take this to the other side, to the left-hand side. Curl of B will be equal to mu naught J free. So this is what we are now Oh, sorry. So this will be the y mu naught minus m. So this is the modification that we are doing because of this material that we are talking about. So this now we can write as a new field H, okay, a new vector H, which we call as a magnetic intensity. And this is different from this B field. And so the Maxwell's equation now becomes mu naught J. Okay, so this we have introduced a new kind of magnetic field now, magnetic intensity, which is different from a B field. Okay, and this is again a consequence of your how the magnetic field varies in a material system. So we will talk about it a little bit in more detail and extend this concept and go into the Maxwell's equation in more detail tomorrow. Any question?
This last will be there.
Sorry?
Uh,
So, please, can I request others to mute, except those who want to ask question? Yes.
just wanted will be there.
Yes. What is the question? I'm not able to hear. I'm not able to hear the question. Can you repeat?
Now I am audible, sir.
Slow, but okay, fine.
Question is that mu in the last equation which you have written, mu 0 will be there, it will not be there. Mu 0
It is there. It is there.
okay. But in book expression not there. That's why it's little confusing.
In book.
For 212, sir.
Which equation you are talking about?
That last equation means the analogous equation in material that
Yeah, curl of H equal to mu naught into J free.
yes, sir.
So curl of H. Oh no, okay, sorry, yes. So what? Because we have divided here, so this I have taken mu naught to the left hand side. Yeah. Yeah. So it is not there. Yes. Yeah. Right. So this is yeah. So the curl of H will be simply this current density. Yeah, the free current density. Okay. Yeah. Okay. Anything else? No.
We'll have another period.
So tomorrow we have another class, no? Yeah. Okay. Thank you.
Thank you.
Thank you, sir.